Here's a couple more examples of making a corresponding acceleration time graph or a velocity time graph and finding displacement. These are a little more involved. So the first thing we'll do is we see that there's a velocity here, but the velocity does change. So this slows down, it accelerates in the beginning here. So we can see here it's slowing down. Then here it's at a constant velocity. And then here we can see it's also slowing down, but at a different rate from what it was at the beginning of this event. So we'll find the slopes of these lines individually, and then we'll make an acceleration time graph from them. So let's take this first segment of the line here. Let's take this first part of the event, these first 5 seconds, and we can see that it goes from 50 meters per second to 40 meters per second. So its velocity decreases by 10 meters per second. This is slowing down, and that takes 5 seconds. So the acceleration here would be -2 meters per second every second, or -2 meters per second squared. Here we see it's at a constant velocity for this part of the line here, which means it's acceleration 0 by definition, right? If it's at a constant velocity, it's not accelerating. For this last part of the line, between 10 and 20 seconds, it goes from 40 to 0 meters per second, so it goes down 40 meters per second, and that takes between 10 and 20 seconds, so that takes 10 seconds. And so we see the acceleration here is -4 meters per second every second, or -4 meters per second squared. So to make this corresponding acceleration time graph, I'm going to make sure I number the horizontal axis, this time axis, the same way it's numbered in the velocity time graph. This is just information for the exact same event. So we have changes happening at 5 seconds, 10 seconds, and 20 seconds. So I'll number this by 5s. So it's 5, 10, 15, 20. And for the first 5 seconds, and then actually before we do that, let's number our acceleration axis. I need to show an acceleration in -2, and I need to show an acceleration in -4, and it doesn't accelerate in a positive direction at all during this. So for the first 5 seconds, its acceleration's -2 meters per second. That would look like that. Between 5 and 10 seconds, it's not at rest. It's at a constant velocity of 40 meters per second, but it is not accelerating. And between 10 and 20 seconds, it has this constant acceleration of -4 meters per second. So that's the acceleration time graph. So that's done. And now we'll look at how to find the displacement. And what we just have to do is break this down into shapes that I can easily find the area of. So here we have this triangle up here. So I'll find the area of that. I know how to find the area of a triangle. And then the next thing we'll do, and we get a different color, is we'll find the area of this rectangle here, because I know how to find the area of a rectangle. And then finally we'll find the area of this last triangle right over here. And I'll find these 3 different areas, I'll add them together, and I will know the displacement. So this is how far this is the object going to end up from where it started. We'll call this delta x1. We'll call this delta x2, and we'll call this delta x3, just so you can follow my work. So we'll find this area, we'll find this area, and we'll find this area here. Delta x1, that little triangle there, the area of a triangle is 1/2 base times height. It runs 5 across. So it's hard to see because it's in yellow, but it runs this far across, and that's from 0 to 5 seconds. So its base is 5 seconds, its height, it's from 50 to 40, so its height is 10 meters per second. And 1/2, in this case I'll do 1/2 of 10 is 5. 5 times 5 is 25. So it's 25 meters, right? A meter per second times a second's a meter. And it's also a displacement, so I know it's meters. Area 2 is just this big rectangle here. This goes, it's just base times height here, or length times width. 10, and it is 40 meters per second high. So it's just going to be 10 seconds times 40 meters per second, which is 400 meters. And the last area is going to be another triangle. So that's this area here. It's another triangle, so it's 1/2 the base. So it goes from 10 to 20 seconds. So it's 10 seconds. And it goes from 0 meters per second to 40. So that's also 40 meters per second high. 1/2 of 10 is 5. 5 times 40 is 200. So if I want to know the total displacement, I add these all up, and I get 625 meters. So first, let's look at this graph. A couple of things are going on. We can see between 0 and 10 seconds, the object's slowing down at a constant rate. And at exactly 10 seconds, if we go here, we can see right at this point that it stops, right? Its velocity is 0 meters per second. Right here it is stopped. And then what does it do? It speeds up in the opposite direction. How do I know it's speeding up here when I'm looking at this line here? Because it's moving away from 0. So this object travels in one direction, maybe to the right. It slows down, it slows down, it slows down, it stops. And then it reverses direction. And it travels, if to the right was positive, then it travels to the left, and it speeds up. But we can also see from the slope here that it speeds up at a slower rate. We can see that the slope is less, so we would expect its change in velocity to be less. So first, let's work on the acceleration time graph. We'll just find the slope of this portion right here. It goes down 50. Goes down 50 meters per second in 10 seconds. So its acceleration here is -5 meters per second every second. Every second its speed changes by 5 meters per second. And then we can take this part of the line right here, and we can see that between 10 and 20 seconds, its velocity goes from 0 to -20, so it goes down 20 meters per second, and that takes 10 seconds. So its acceleration here would be 10 meters, or -2 rather, meters per second every second. So let's make this velocity time graph over here. We need times of 0. The next time something happens is at 10, and the next time when it comes to rest, it's at, or we stop collecting data, it's at 20. So we can just put 10, 20, and we can see for the first 10 seconds, it's got a constant acceleration of -5, and then it has an acceleration of -2. So do -2, let's say 3, 4, -5 would be down here somewhere. So for the first 10 seconds, it's -5, and for the next 10 seconds, it's -2. And one thing to note in this is that even though its acceleration is negative the whole time, its velocity isn't. So its velocity is positive for the first 10 seconds, negative for the next 10 seconds. It slows down, and then it reverses direction and speeds up, but its acceleration is negative the whole time. Now let's find the displacement. The displacement is going to be the area under the curve. So we'll take a look at this area first, up here. It's from the line to the horizontal axis. And then we'll look at this area from the line to the horizontal axis. Sometimes people calculate funny areas, but just it always has to be to the horizontal axis. So we'll call this delta x1, this area here. We'll call this delta x2. We'll add them together and we'll find the displacement. So let's find delta x1 first. It's a triangle, so its area is 1/2 base times height. The base, it goes from 0 seconds to 10 seconds. And the height is 50 meters per second. 1/2 of 10 is 5. 5 times 50 is 250 meters. The second one is also a triangle, so it's also 1/2 base times height, and it's also 10 seconds across. It goes from 10 to 20, so that's 10 seconds. But the height, it goes from 0 meters per second to -20 meters per second. 1/2 of 10 is 5, and 5 times 20 is -100. So watch your signs. And we can hopefully look at this and know that we're going to end up with a positive displacement overall. The area above the horizontal axis is, just to look at it, it's bigger than the area below. So we expect a positive displacement, and we get one. 250 plus -100 is positive 150 meters, and that equals our displacement.